Welcome back to our session on measuring information storage in complex systems. In our previous short videos in this session, we've looked at introducing the primary measure of information storage that we'll use, the active information storage, and how to use that with the JRDT toolkit. In this final short video of the session, I'm going to give you some background to one of the activities associated with this session, and also talk about a complementary measure of information storage known as the predictive information. Let's start by giving some background to one of our activities. Cellular automata are arguably the most important canonical system from the field of complex systems when we want to talk about information processing or computation in complex systems. Much of the focus about how computational information processing occurs in cellular automata focuses on emergence structure. What I mean by that are the structures known as domains, blinkers, particles, gliders, domain walls, and collisions. Let's look at what we mean by each term there. This diagram is looking at ECA Rule 54, and then what happens when we filter for the emergence structure in that rule on the right here using the technique of Wunsch. This is a figure from that paper. The domain structures here are the background patterns that remain unchanged if we only have the domain pattern and nothing else interfering with it. Okay, so we can think about that as the spatiotemporal background pattern. Blinkers are one part of the emergent structure that appears against the background. They are the part of the emergent structure that does not move in space. Okay, so here we've got space going across the page, time going down the page as before, and we can see the blinker structures here and so on, which appear against the background domain but do not move. They stay static in space. Particles are the emergent structure that appears against the background domain that do generally move in space. So we can see some of those here, and here. They're a bit hard to see in the raw CA. We can see them much more easily if we look at the filtered values. Okay, I won't go into how the filtering was done by Wunsch here. We'll look at our own kind of filtering later on. Particles is a kind of all-embracing term. It can be used to include blinkers as well, but it usually refers to the moving structures here. The regular kinds of moving structures are what we call gliders. Irregular moving structures we usually call domain walls, and we can see those in different rules, such as Rule 18. Collisions between these emergent structures occur as well, and that's where a lot of the interesting dynamics happen. You can see here a collision between a static structure and a moving one, creating some change to the dynamics. You can identify a collision down here as well, and even over here, and obviously they're much more easy to pick out when we look at the filtered CA. In terms of information processing, the emergent structure are quite important because they've been conjectured to have significant computational roles. The background domains and blinkers are conjectured to represent information storage, particles information transfer, and collisions information modification. This makes a lot of sense intuitively because we can see that there's periodic temporal patterns in blinkers and domains, which align a lot with the way we've already been talking about information storage. We can imagine that particles, as they move across the CA, are communicating something about the dynamics from where they started to where they end up. Okay, it's an effect of that earlier dynamics on the later dynamics, so they seem to represent information transfer. And collisions seem to represent some kind of decision in the dynamics about what happens next, and information modification. You can read more about those conjectures in the papers listed as references here. In our associated activities, I want you to try the active information storage calculator on some sample cellular automata data. There are two particular things we're going to do. We're going to look at computing the appropriate embedding length for the information storage calculation using effectively the auto-embedding measures that I've talked you through before. So we'll come back and answer that question we looked at earlier. What should the embedding length be for the CA here? We'll then use that computed embedding length to then compute local active information storage values and look at how the information storage fluctuates in space and time across the CA and see whether there's any relationship between those information storage values and the emergent structure. Do the domains and blinkers indeed have strong information storage values? I'll give you a brief spoiler here. You can skip over this if you want to try the activity yourself, but you can probably guess what the result is going to be. And that is basically that blinkers and domains are the dominant information storage entities, as we can see in this plot here from some of my previous work. Moving on then, I want to show you an alternative measure for information storage. This is the predictive information, which quantifies how much information about the whole future of a process can be found in its past state. Okay, it's a mutual information between that past embedding vector and a future embedding vector, ideally in the limit as their lengths diverge, but we can take finite case samples of those as well. This measure captures all of the information storage in the past that is used at some point in the future. Okay, and we can see that on the diagram here. It could be a part of the past that comes in very, very late in the future. This contrasts with the active information storage that we focused on before, which measures only the part of the information storage that's in use in computing the very next value in the future. And so it's a first order component of the predictive information, and indeed is a lower bound on it. We are generally more interested, from my perspective, in the active information storage because it focuses on the computation of this next value, rather than the whole future, because the questions that we were focusing on with information dynamics was all about the computation of the next value of our time series. Indeed, because of that, it's complementary to the measure of information storage that we'll look at in our next session, because they both focus on the computation of the next value rather than a whole multivariate future. The predictive information is strongly related to another measure called the excess entropy, which quantifies the total structure or memory as a slowness of the approach of the conditional entropy rate estimates to their limiting value. We can see this in the same plot that we looked at earlier regarding the entropy rate. The excess entropy pops out as this quantity here. If we take our the slope of our line of the approaches of the entropy rate estimates to their asymptote, it's the intercept of that asymptote there, and that quantifies memory as the slowness of the approach of these estimates to their limiting value. Importantly here, it's equal to the predictive information for stationary processes, so we can understand it very simply as a measure of information storage from that perspective. Importantly, this is implemented in the JRDT toolkit using the predictive information formulation. It's not in the autoanalyzer, but you can look at the calling pattern used on related methods such as the active information storage and bring those across to use with the predictive information estimators. So that brings us to the end of our session on information storage. We've examined how information storage is characterized principally through the active information storage, as well as looking at the predictive information. We've used the JRDT autoanalyzer GUI and extensions of the code there to analyze how information is stored in complex systems datasets, in particular with that activity about cellular automata. Coming up in our next session, we're going to look at the complementary measure of information transfer in complex systems, looking at that in particular as the next stage in our modeling of the information processing taking place in a complex system.